Hi, welcome to Organic Chemistry Tutorial Sheet 5. This is part 2 of Tutorial Sheet 5. Let's get into this video. So we already solved question 1 and question 2, and now we're doing question 3. So let's move on. So predict the products of the following reactions. So A has this. So there's a double bond here and here. And you're reacting it with hydrogen chloride. So what is going to happen is that this double bond will come and get this hydrogen here, and the chloride will leave. So what you have is this. So the hydrogen will be added here, and there will be positive charge there. But you know that in solution, you have chloride that is negatively charged because it went with the electrons at this stage. So this chloride will come and attach there. So your final product will be this. So this is what we call a 1,2 product addition. Why? Because the hydrogen attached on this carbon, carbon 1, and then the hydrogen, the chloride attached immediately the carbon that is adjacent to where the hydrogen attached. So this is the first way it can occur. Second way it can occur is like this. So react it with hydrogen chloride there. This in first step will attack this. The chloride goes, and then it will form this. The hydrogen will be added there. The positive charge will be here. And then this double bond is going to follow the positive charge, so it will move to here. So what you have is this. The double bond will be here, and then the positive charge will be here. The chloride which left in solution here will then come and attack there. And then the product will be this. So this is what we call a 1,4 product addition. 1,4 addition, because the hydrogen attached here on carbon 1, 2, 3, and then the chloride attached on carbon 4. So that is two ways in which A can react. Let us go to B. So B, they're saying how can this react? So they put this in D2, D to D, like that. Okay, so let me check. It's DC. It's DCl, not D to D. First thing, so this will attack that there. And then this will leave. So what you find is this. So the D will be added here. And then here there will be positive charge. and then the chloride in solution that left will come and attack here. So your final answer will be this. So the D will be there, and the Cl will be there. So this is a 1,2 addition. Another way it can react is where you have so when the first step takes place, where this will come and get that, this leaves, and then you form this. So the D is here, positive charge. This bond will move to here. So you form this. Double bond here, and then the positive charge will be here. The chloride that left in solution is negatively charged, so it will come and join here. So you have this product here. So you've seen D is added on carbon number 1, 2, 3, chloride on carbon number 4. So this is a 1,4 addition. That is a 1,4 addition. All right. So B was saying suggest a structural explanation for the fact that 1,2 addition reaction of 1,3 butadiene and hydrogen bromide occurs faster than the 1,4 addition. And then how can you account for the fact that the 1,4 addition product is more stable? So the 1,2 occurs faster than the 1,4, but the 1,4 is more stable. Let's work this out. All right, so let's draw this. So 1,3 butadiene and hydrogen bromide. 1,3 butadiene. So you're reacting. 1, 2, 3. The 1,3. So reacting with this. So the first reaction that occurs is this. This goes, and then it will react like this. The H will come here. This will be positive. The bromide in solution, which is negatively charged, will come and attack there. So this will be the 1,2. So this is the 1,2 addition. And then the 1,4 occurs like this. So this comes, gets that, then this goes. But then this changes, goes there, so it becomes this. Positive charge changes there, and the bromine come and attach there. So the product becomes like that. So this is a 1,4 addition. So now they're saying that the 1,2 is faster, but the 1,4 is more stable. What is the reason? So this is because in the 1,2 addition, look at where the positive charge is. This is the more substituted allylic carbon. So the reaction will be faster. So because this is a secondary carbocation, and then this is a primary carbocation. So this one has more positive charge than this one. So the secondary carbocation that is formed in a 1,2 addition has more positive charge than the primary carbocation that is formed in a 1,4 addition. But then in the 1,4 addition, the double bond is more slightly substituted than in the 1,2 addition. Hence, it is a more stable alkene. So the reason why reaction 1 will occur faster than reaction 2 is because the carbocation here is more positive than the carbocation here. That's why this one will react faster. But the reason why reaction 2, the product that is formed here, is more stable than this product is because the double bond is more substituted. Look at the double bond here is between two secondary carbons. Secondary carbon here, secondary carbon. But then here, the double bond is between a secondary carbon and the primary carbon. So the double bond in the second reaction is more substituted. That's why it's more stable than in reaction 1. Okay. So C says, what product would you expect from the reaction of 1 mole of 1,3 butadiene? So same 1,3 butadiene with 1 mole of chlorine. So this one would either give you a 1,2 substitution, a 1,2 addition, or a 1,4 addition. So it either be this chlorine here and there, or it will be a 1,4 chlorine here and chlorine there. So this is a 1,2 addition. This is a 1,4 addition. Okay, so this is number 1. Number 2, 2 moles of chlorine. Then you have 2 moles of chlorine. It will be everywhere, the double bonds will be broken. So you have a chlorine here, a chlorine here, a chlorine there, and a chlorine there, because there are 4 chlorines. Number 3 is you react this with 2 moles of bromide. So there are 4 atoms of bromine here. So everywhere to be substituted. So bromine there, bromine there, bromine there, bromine there. That's what you expect. So this was number 3. Number 4, you react this with 1 mole of chlorine and water. So what you would expect is that you either have a 1,2 substitution. So you either have this, or you have a 1,4. Or you have here chlorine, and you add an OH from water here. So those are the three products that you would expect in this reaction. Okay, so this says when 2-methyl 1,3 butene, let's write this down. 1, 2, 3, 4. So 2-methyl, this is a methyl on carbon number 2, 1,3 butadiene, 1, 3, undergoes a 1,4 addition of hydrogen chloride. The major product that is formed is 1-chloro-2-methylbutene. Little or no, so they're saying the product that is formed is this. Formed is 1-chloro 3-methyl, so methyl is here, 2-butene. This is the product that is formed. But not 1, 2, 3, 4. But not this one. 1-chloro 2-methyl 2-butene. So no product in this. This is not formed. So now they're saying, how can you explain this? So how you can explain this is that, first of all, what is going to happen here? This reaction, how it's going to take place. This will react with hydrogen chloride like that. This will come, attack the H there, get the H, the chloride will go, and then you're going to have a carbocation there and the double bond there. Okay. And then this double bond is going to shift. It's going to come here. So the resonance for this will be this. Positive charge there. Okay. So the chlorine which left here would then come, which is negatively charged, get attracted to this positive charge, and then form this product, which is this product here. So this is 1-chloro 2-methyl 2-butene. So this is 1-chloro 3-methyl 2-butene. So the product 1-chloro 2-methyl 2-butene will not form due to its non-hybrid contribution in the resonance. In the resonance, it won't. There's no way chlorine will come and attach here. There's no way chlorine will come and attach here. So there's nothing like in the resonance between these two, this and this. There's nowhere where chlorine is going to attach at this carbon here. Okay, there's no way where chlorine is going. So there's no hybrid in the resonance where this can form. There's nothing. That's why it is not formed. So E, saying there, the hydrogen atoms attached to carbon 3 in 1,4 pentadiene. So this is pentadiene here. Carbon 1, 2, 3, 4, 5. 1,4. So there's a double bond on carbon number 1 and on carbon number 4. 1, 2, 3, 4 here. And they're saying that these hydrogens here are usually susceptible to abstraction by radicals. How can you account this? How can you account for this? So the high susceptibility of the hydrogens on C3, which is this one, this carbon here, on C3 of the reactant are allylic carbons, hydrogens rather. These are allylic hydrogens. So when they are abstracted, the result, when abstracted, when they are removed, they result into the formation of secondary allylic radicals, which are very stable. Okay, so they form very stable radicals. They form very stable radicals. So if you remove this, say you react this with a chlorine radical here, this will contribute one, the other one will go here. So this will result into this, into a radical. The reason why this forms is because C3 here, carbon number 3, is an allylic carbon. So because it is an allylic carbon, it is going to form a very stable radical. If you were to draw the resonance for this, it would be this one contributes one here, this contributes one here, the other one goes there. So it would be this. It would be like that. The other resonance that can form is this. That is the other resonance that can form. So it forms a very stable radical, because the hydrogens here, these hydrogens are allylic carbons. And remember, allylic carbons are very stable and very reactive carbons. Okay. F says, can you provide an explanation for the fact that the protons attached to C3 on 1,4 pentadiene, 1,4 pentadiene, these ones, so they're saying that these protons, the hydrogen protons here, are more acidic than the ones that are attached to methyl, than the methyl hydrogens in propene. So propene is like this: 1, 2, 3. The methyl is this one, the hydrogens that are attached here. So account an explanation why these hydrogens here are more acidic than this. Well, it is because these hydrogens on the C3, this C3 is a substituted allylic. So these are substituted allylic carbons. So C3 is a substituted allylic carbon, whilst this carbon here is a non-substituted. Allylic carbon. So you expect that the hydrogens on a substituted allylic carbon will produce more acidic hydrogens than the ones that are in a non-substituted allylic carbon. Okay. Okay, question 4 says provide a mechanism that explains the formation of the following products. Okay, so let's start with A, question 4A. So question 4A has given us this and in concentrated hydrochloric acid. So what is going to happen is that this oxygen will get this hydrogen there, then this will go. So then you have a protonated oxygen here, so it will be positively charged there. When it's positively charged, this will become a leaving group, a good leaving group, so it will leave. So what you have is this. Positive charge there, here, like that. So now these can form resonance structures. This can form resonance structures. The resonance structures would be such that this double bond can follow the positive charge there, so it can also be like this, positive charge here. So now the chloride in solution that left here can either go and react here, or it can go and react here. So when it reacts here, the product will be this. When it reacts here, the product will be this. So that is how these two products are formed. That is how this and these products are formed, because of resonance. Okay, let's look at B. So B is that provide a mechanism of how this product is formed. You react it with this compound here to form this. So the mechanism is such that it will go like this. So what will happen, first of all, is that the nitrogen has a lone pair of electrons here. So these lone pairs of electrons will attack here, and then these electrons will move and come here, and then these will go there like that. So what you form is this. Oxygen, double bond, and then this will now have two hydrogens and the CH3 here, so it will be positively charged, like that. You can form a resonance here where these can collapse here, and then these can come on this, that carbon there, so you can have that as a resonance structure. And then there will be pairs of electrons here negatively charged, and then this still be positively charged like that. Okay. And then what will happen is that one of the electrons will be deprotonated. Okay. So reaction with these, there was methanol in solution. So in this reaction here, in this product here, A, the nitrogen had two hydrogens here. Let me just write them like this. So what will happen is that the ethanol will come and deprotonate one hydrogen here, and then this will go there, and then it will form this structure here. This is still negatively charged. So the ethanol will now be protonated. This will go back to its original shape, and then this double bond will collapse and get the hydrogen from the ethanol. Then that will go back to that. And then the product that you form will finally be this product here, which is this product. So that is how this product is formed from this reaction mechanism. First step, the lone pair of electrons will come and attack the double bond. Double bond will shift and will go between this carbon and the carbonyl carbon, and the pi bond between the carbonyl carbon and the oxygen is going to break and form this product A here. Okay. And then the ethanol will come and deprotonate the nitrogen. Then lastly, the negative charge on the oxygen will reform the double bond, and then this double bond will go and attack the protonated ethanol, and that's how this structure is going to be formed. See, write the mechanisms that account for the products of the following reactions. This is a lot, but this will happen like this. So we must know that this is a double bond here. Reacting with this one here. So what is going to happen is that this negative charge that was here, minute, so know that this carbon here in the question has a lone pair of electrons. So this lone pair of electrons will come and attack here. It will displace the double bond. This double bond will move to here, and then this will go like that, will break. So what will end up forming is that this reactant is going to join here. So it will join there. Okay, and then this will be there. So carbon 1, 2, 2, 3, 4. So there's an oxygen here, and the electrons broke here like this, so this will be negatively charged like that. And then this one here, there's an oxygen, then there's another carbon that is attached like that. So remember, there's ethanol in this and then there's a double bond here that is formed like that. So what will happen is that since there is ethanol in this solution, this ethanol here, which has an H, this negative charge will go back and reform the double bond, and then this double bond will come and it will get the H here from ethanol. So the final product will be such that the double bond is going to form from here, and then here it will be a single bond. So this will go back to this. That's how it will be. That will go back to that. So let me just write it. The product will be double bond here, and then here, so that will be the product. That will be the product. So that will be the reaction mechanism of this reaction. And then for B, the reaction mechanism will be this. So we have this compound here, reacting with so first thing, the lone pairs of electrons on the nitrogen will go and push this double bond to here, and then this will break. So what will happen is that there will be addition of the nitrogen, double bond here, then the nitrogen will be added here. This nitrogen has got CH3 attached to it, and then it has an H here and another H here, so it will be positively charged. So it will be positively charged like that. But what will happen is that this double bond will come and it will get, so this will reform here to form a double bond, and then this double bond will get this hydrogen here, and then this our electrons will collapse on the nitrogen. So what it will form is this. So this one has a lone pair of electrons again. So these lone pairs of electrons will again react with this. So this will come and react here. This will push this double bond here. This will go there. So what you have now is this structure. You have an N in between. And then even this side. Negative charge, like that. But here you know that you have an H and then you have a CH. So this will come, drop here, and then this double bond will get this. So what you end up forming, is this structure. So from here, from A, you go to the final stage, which is this. So that is how that product is formed using this reaction mechanism. Okay, D says carboxylic acid derivatives undergo nucleophilic acyl substitution reactions on the carbonyl carbon. Rank the following sets of carboxylic acid derivatives in order of decreasing reactivity towards this reaction. Explain the rankings. So for A, how it is that esters, amides are the least reactive. This. So C is less reactive, followed by, okay. So the least reactive here is the acid itself, A, followed by C, followed by B, followed by E, followed by D is the most reactive. Why? Because the nucleophilic acyl substitution reaction is dependent on the reactivity on the leaving group. So it is dependent, so reaction dependent on leaving groups. So the best leaving group is the most reactive. So this one here is the best reactive group. That's why it's the last. And then for B, you follow which one is the best leaving group. So you see this is the same. But you see the fluoride here is the best leaving group. So it's the most reactive. It's the most electronegative. So D is greater than B, which is greater than C, which is greater than A. Fluorine is the most electronegative, followed by chlorine, followed by bromine, followed by iodine last. That's why this is it. Okay, so this was part 2. We'll get into part 3 later, where we're going to do question 5 and question 6. See you in the next video.